Alright, should be good. So this is for the benefit of Justin, who is probably buying a house right now, which is so exciting. So basically we've just been kind of getting some technical things ready, Kate. As far as what we're going to do for class, my intent is to basically cover some of the things that you guys were able to research. Just spend a couple minutes going over what you found interesting, things that you can share with whoever's assigned the next area if you found something. So, yeah, basically you should have researched a little bit into what you need to write on for the wiki, and basically how it's going to go.
I didn't know that I was supposed to have researched it by now.
Okay. Did you watch any of the videos or any of that? No?
I just did the paper homework. Because I emailed you about it and said I would have it done for this Wednesday, and you said that it wasn't due till the next Wednesday, so I haven't done it yet.
Okay.
Sorry about that.
That's fine. It was a little bit confusing, so I suppose right now is a good thing to kind of cover a little bit better the expectations since I made that change. So if you can see the schedule that I've got here, basically what we're going to do is we're going to discuss the topic and what we researched for topic 1. If you don't have anything, Kate, that's fine. We can just have a discussion about it. So we'll do that for the first 20 minutes, maybe, depending on how much we have to cover. And then we'll cover topic 2, which this week is understanding how signals are represented mathematically and how we can kind of affect them. And then next week, the wiki page is actually going to be due, so I forget who got assigned to what, but this first section, introduction and description, examples in the real world, why is this topic important? What I'm looking for is a couple paragraphs for each. For introduction, just kind of a brief overview of what the topic is, and how it kind of relates to signals and systems. Examples, kind of go through what the example is, why it connects to signals and systems, so maybe do a little bit more explanation from the introduction, and then go on to the next one, why is the topic important. Okay, someone's got feedback.
Yeah.
I can barely hear anything.
Give me a second here.
I don't think it...
I don't know why it'd be me. I've been talking for how long and I haven't had anything like that. Nothing.
Okay, it's not my mic. Kate, can you mute your mic quick?
What do you want me to do?
So go on to Skype, the Skype screen, and there's a microphone down at the bottom.
Let me mute it?
Yep.
Does that mean I don't have to talk during talk?
Well, I just want to see who's having the feedback.
Oh.
Okay. Kate, you have the feedback issue.
Should I leave it muted? Type or something? Well, now it's not muted. Can you hear me?
Yeah, I can hear you.
It's still gone. So how does that make any sense?
It might be from when I'm talking or Charlie's talking, and it might just be too loud.
It doesn't have to be on video.
Because Charlie doesn't have a webcam.
Ooh.
Hey, come on now.
I don't have a webcam either.
Yeah. Anyways, last topic, why is this topic important? Just kind of explain how the real world examples kind of connect into it, why it's important for us to know it, and that one's kind of the harder topic to cover, to make a decent amount, so that one I'm kind of expecting less rating, but that's kind of my expectations.
Sounds good to me.
So yeah, next week, writing for this first section of the wiki is due. And that'll be due at class, so I'll check it at the beginning of class. So, yeah.
Did you say a few paragraphs?
Yeah, 1 to 2 paragraphs. There's a reason why I put it under fundamental knowledge. I'm not expecting really deep, in-depth explanations of anything. This is basically to get the basic idea out so that someone could read through this and know exactly what's going to be covered in class.
Do we have to write in paragraph style?
You don't have to if there's certain ways that you can think of that you portray the information better. I think paragraph form would be easiest.
I'm gonna draw pictures.
Whatever floats your boat.
He's from Cali. I don't think he can actually write.
So
I got a badass set of crayons, alright? But I never go outside the lines.
But besides that, are there any more questions about kind of the expectations?
Nope.
Can we put pictures in there or graphs or anything?
Yep.
Just...
You can put whatever you want in there. I'm looking for about a paragraph's worth of information and explanation. So if you can explain it with graphs, you know, with figure headings, that's fine. Just get the information across. And
Oh, I have another question. Sorry.
like I said, we're basically gonna go through all of it, and then at the very end we're gonna go through it again and review it, see if there's any changes we want to make, and that final quality will be your wiki participation grade. So you're graded on participation for doing the wiki on time, and then you'll be graded on quality later. Sound good?
Can you hear me?
I can hear you, but you still have the feedback.
Huh? Oh, okay. I was trying to ask you a question. I didn't know if you were just ignoring it. Couldn't hear me.
Oh, no, I couldn't hear you.
Oh, okay.
So what's your question?
Jeez, it's like totally blowing me up. My question was, isn't there a place on our wiki page that you can put the videos, like actually on the page, instead of just emailing them to us?
I think so. I think I can embed YouTube videos onto this.
Maybe did it wrong.
Okay.
I just think it's kind of nice if people use it in the future.
Yeah. And that might be something that we have to look into. I'm not sure how much I like the idea of having me be a quote-unquote teacher for anyone that watches the wiki, but that's an option. We can look into it too. And if there's any videos that you find that you want to add, I can look into how embedding works.
Just meant the videos emailed to us, like the ones from YouTube.
Oh, yep. Yeah, we can, I'm pretty sure there's a way to embed videos onto this, yeah.
Can I just like type if I have a question, then shut my microphone off?
I don't know if I'll be able to see it right when you type it, though.
You can't hear me, what I'm saying.
Yeah, it cuts in and out quite a bit. Well, if you do mute your mic, and
I'll text you if I have a question or something.
that works. Okay. I suppose we will start with the discussion of topic 1. Charlie, I know that you went through quite a few of the videos you were saying. So, did you just look into kind of your specific area, or did you look into all of the areas?
Well, I've been doing a little bit of research on just reading signals and systems information, like kind of where it goes and where it's used through.
Okay.
So I haven't got very in depth with my specific one yet, but I've been watching the videos as well. So.
Okay. I suppose, is there anything that you feel is good for some introductory information or examples, or just kind of reasons why the topic's important?
Why the topic's important?
Any of the 3 areas that we're going to cover in the wiki. This is basically to get information out.
Are those first 3 you're talking about that you're next to?
Yep.
You there?
Yep. I'm here.
Okay, sorry, kind of cutting out. You said the first 3, or the ones you were talking about, why they're important.
Just kind of some introductory information, examples, or reasons why it's important, just so that whoever's got that topic can kind of look deeper into it.
Oh, yeah. Yeah, from what I was getting at, there's a ton of uses, but the one I was kind of interested in was its usage in the audio field, audio broadcasting, and reading on a bunch of stuff like that. I was reading that it's used in audio, speech, image, video, wireless communication. That's just reading off a list I have up right now.
Okay.
And I'm sure, like Kate said, you're using it for for monitoring your systems too as well, correct? So there's just a ton of different uses. It really seems like it goes wherever, and especially on things where there's a lot of information coming in at once. Filters, signal compressors, digital. So it seems like basically wherever you want to use it, wherever you're interested in, there's probably a usage for it.
Okay. Yeah, that's a really good area to start. Audio, especially. Talking about analog and discrete. The example that I had on the homework last week was the analog signal cut into a vinyl record versus the digital signal that's etched into a CD. That's one area. So you've got analog and digital signals in music that we were able to physically see, and then signal manipulation, auto-tuning. Basically what auto-tuning does is it takes all of the vocal signals and kind of smooths them out and makes them kind of weird. And you can adjust how that manipulation happens. So that's a really good example for the real world section. Kate, I don't know if there's anything that you want to add to that discussion. next. One example of why it's important: in many industries, they collect and interpret signals to stay within environmental regulations. Like at my job, Kate's, we monitor nitrous oxide through a monitor that is transferred into a signal on IP21. So yeah, that's a lot of information that Kate's bringing in and kind of analyzing, and if there's a change that they see they need to make, they can alter what they're doing to change that signal. And they can do that mathematically too. There's a lot of research that can be done to understand how their system affects different levels, particularly the nitrous oxide levels. So that's another great example, Kate. So yeah, are there any questions about how this is kind of going? This is generally the direction that I want the first part of each class to go. So next week, basically research a little bit deeper into understanding how signals can be represented mathematically. That one's going to be a tough one. There aren't going to be a lot of resources out there because this is basically equation manipulation at a very basic level. It's basically Algebra 2 understanding what different areas of an equation do to a signal when you manipulate it. Excuse me. So I guess that brings us to the topic that we're looking at. We discussed that there are different types of signals last time, and just to begin tonight, I kind of want to go over some of those signals. So obviously the one that we talked about, one that we're really familiar with, sine. In this case, we're going to do it to t because it's a signal, and by our definition, a signal is anything that's occurring over time. So you got that type of a signal. And basically, the way that I see it, sine kind of represents any known equation that we have. So y equals mx plus b. That's kind of on the same plane as sine. Another pretty common one is u of t, which is a unit function. And basically that's an amplitude function. So basically if u of t is 1, your amplitude is going to be 1 across all points of time.
So basically like a motor.
Yep. So basically this is the DC signal that's going into a electric motor. The motor runs at a constant speed unless the system is altered.
That kind of goes into where that video covered with wherever, as long as you know the response that a system will react to, then you can accurately model it with that.
Yep, and that's basically going into, that's not what I want. Going into next week's topic, basically systems, system properties, and even further into understanding how signals are utilized to identify unknown systems. So, Charlie, if you can kind of remember that for 2 weeks from now.
Will do. I'll try. I'll do my best.
That's kind of where we're going to cover that a little bit more in depth, but it's a good thing to bring up. So, unit function, it's a constant function. we also have delta t, which this is our discrete signal. So I can't accurately draw what this is because delta t is actually just a point right here. So it's basically that discrete point in time taking a measurement. So if you remember back to last week where I took the sine wave and broke it into a discrete signal, all of those points were delta functions, different delta functions. Am I getting too small for this on your screen?
No, it's basically my full screen.
Okay. From that point, we also have a pulse function, a lot of times also called a big delta. And thinking back to pulse width modulation from Circuits 1, which is so wonderful, that's just a unit function, but for a given period of time. And typically what we do, pulse functions are a combination of unit functions. So this is kind of a more complex version of just writing and just shortening up a bunch of unit functions. So if we want to work in them, we'll probably end up working with unit functions because they're easy. I think that's all of them. Yep. So those are the basic functions that I worked with when I took signals and systems. Basically, you've got a couple analog signals, the discrete signal, and that's kind of what we have to work with. It's not much, but you can make some pretty crazy things. You can make a sine function out of delta functions. So there's a lot of powerful things that you can do with this, and it's kind of useful to certain people. Today I'm kind of going to be working with this unit function to kind of make a representation of what we're going to be talking about. And a lot of this, again, is going to be math review and understanding how manipulating an equation manipulates a graph. So if I have, well, I suppose it might be easier to work with pulse functions. So if I have this function, I'm just going to call it P of t. This is at 1, this is at 1. And your amplitude is equal to P at t. How might you go about amplifying the signal? Mathematically.
Longer time period, or?
I'm talking amplitude. So how would I make this 1 a 2?
Cut it in half.
Can you kind of elaborate if I cut it in half?
Are we talking this area is staying the same?
No, we're talking just take this entire graph and bring it up to...
Multiply it by something then.
Yep. So basically amplitude is controlled by multiplication and division of your core component, the entire equation. So if I were to have a sound wave, and I wanted to make this entire thing bigger, basically what I'm going to do is just multiply the entire equation. So text. So that's our first one. Amplification and reduction, you're multiplying the entire equation. And I spelled divide wrong. So that brings us to the next one, which Charlie, I think you were trying to get at. How do we kind of expand it horizontally? Again, we're just going to keep it at 1 and 1 to begin with. And how addition is one way. So basically, if we want to take this from 1 and do it to 2, you can basically do how it's represented here and add 2 equations together. But there is another way of doing it. Any thoughts?
Subtraction and negative.
What was that, Charlie?
Subtract the negative.
So you're adding.
I'm sorry. Got it.
Basically, what you can do is manipulate this time variable. So you can take this, and every point, if you divide it by 2, wait a second, am I thinking about this right, or am I skipping to a different one? Let me check. This is why I'm not a teacher.
Just pull the Bart, drink coffee, and say,
Oh. Well, while I look up this, can you give kind of an example of why we might want to change amplitude? Well, obviously amplification. Get some examples of amplification and reduction that we might see in the real world.
If the signal is too small to really read the differences, or the opposite, if the signal is too large of a scale to really monitor.
Okay. So yeah, that's basically, if we're looking at op amps in terms of electrical. We're taking a really small signal, like in a sensor, and we're amplifying it to see the effects that we actually are having. Can you think of any kind of mechanical applications for that?
Or going to to amplify it or something like that?
So, if we have a certain response in an engine, let's say you hit your peak,
Horsepower at whatever.
you hit your peak horsepower at a certain point in time. If you want to increase that horsepower at the same time, one way that you can do that is change your system and, let's say, add in a supercharger. The response time might be the same, but the overall horsepower will be increased. Kate, do you have your microphone on?
I think she fell asleep.
Yeah, I'm sorry.
Oh, yeah, I guess you glitched up, so it looked like you were in the exact same position for a while.
Yeah. Kate has awesome internet like I do.
Yeah, you're like head down for the last like 5 minutes. Like it looked like you were sleeping.
Okay. So, I have this backwards. It's not dividing, it is multiplying. So, to expand an equation from 1 to 2, 2t. So, the opposite is true if you want to shrink this down to half, half t. So that's, you manipulate what you're putting in to change the overall shape of the formula. Kate, you brought up having, in addition to the equation that's already there, so what you might have is this initial equation plus that same equation shifted over right, which kind of brings us to the next one. How do you think we shift these equations? Left and right, I should say.
If start from a different time frame, I guess, or a different position. So basically, you could start monitoring instead of during the increase. You would instead monitor at normal speeds. So.
Okay.
That makes sense, but not really either.
Yeah. Mathematically, the way that we shift equations left and right is by adding or subtracting from t.
Oh, I got one. Would work. Like capacitors, you put several in, and then you're actually able to smooth out the curve to represent more of a straight line feature. So shifting that reaction point over, I guess.
I suppose, yeah. Depending on the capacitor that you're putting in, depending on how fast it charges. The way that I was kind of thinking about it is, if I take this, how do I shift it from this position, keeping the same shape, over to this position? Is that kind of what you were talking about, Charlie?
I was trying to, but I don't think I'm going on the right note of it. So
Okay.
let's hear the correct way.
Like I said, mathematically, the way that we do that shift is by adding or subtracting from t. You're right, just changing what time frame we're looking at. And this one's kind of counterintuitive because a minus is shifting to the right. And the way that I always try and remember it is that this point is to 2. So if we look back to the original equation up here, this point is at 1, 2 minus 1, so that's the point that I'm looking at. Make sense?
Yep.
So if I want to shift left, I'm plussing, or adding, plussing. Working in negative time is always interesting. So one example for this might be I've made a recording, but I've got 2 seconds of silence, and I don't really want to just try and take out the raw data. What I can do is I can shift it all back those few seconds, and it'll start where I want it to, but I'll still have that data. So that's one application for it. Kind of like dropping a needle a couple seconds into a record is what a physical analogy might be.
Sounds good to me. It makes sense.
So let's see here. Alright. No. And this paint is amazing. Whatever. Doesn't matter. So this is overall just basic equation manipulation. So how might I flip this about the x-axis? So take this equation, flip it over so that it's exactly opposite.
Divided by -1.
Yep. So again, you're multiplying by a negative coefficient on the entire equation to make the entire signal opposite. That does mean that your sine wave is going to change, and you'll still have positive parts. So
what would be some of the uses for actually making a negative signal? Sorry if I'm dropping.
One example that I actually gave last week, working with Daktronics, if we were to put in a program and an image showed up upside down on the display, but we couldn't alter the, due to cabling or whatever physical means, we could actually take an equation and invert that and make it mirrored but right side up.
Okay, that makes sense.
So that's one example, as rare as it might be, a way that this inverting of signals might actually be useful. We didn't really cover inverting about the y-axis too much. Well, yeah, basically inverting at the y, instead of having your negative here, you'd have your negative here. So I'm going to get rid of all this. Oof, whatever. So if I have this equation, sine of t, then that equation would be sine of negative t. So pretty much everything that we've been covering so far is going back to algebra, basic, adding, subtracting, multiplication, division of components, different components of an equation. And they affect signals in different ways because they're just graphs. There's a lot of different uses for it, particularly in the audio industry, is definitely the key player on this one. Amplification is useful in a lot of different situations. Widening and narrowing of signals, I suppose could be useful in looking at very quickly sampled information, trying to see where high points and low points are.
Or very, very slow changes.
Yep. So yeah, if you want to take data that you collected over an entire year and see everything on a small scale, you could narrow it down. So I suppose one example might be earthquakes. We take years of data for earthquakes to get very, very few actual spikes, to see how that kind of correlates and if there's any kind of patterns that show up. We might squish that data down and be able to see kind of a pattern that's showing up. Then we can match that pattern much more easily on the small scale and then re-expand it back out. So that's a very good example, Charlie. Then you can combine all of these different components to make drastic changes to signals. So I have an equation here that we did at the beginning of class when I was taking this, and it looks something like this. So, what could this equation possibly look like? Basically, we're going to be actually adding together sine and, or actually multiplying, not adding, sine and u of t equations. So because u of t is 1 across the board always, if we just straight multiply sine and u of t, we would get a standard sine wave. But because we have this missing section, we actually have to have a more finite example. So this equation actually turns out to be sine of t multiplied by u of t. This is 2, this is 4, minus u of t minus 2 plus u of t minus 4. That's a really long minus, but so obviously we know that sine of t looks like this is the more interesting part. So we're adding and subtracting different equations, but they're just shifts of the same equation. So this equation actually gives us something that looks like this. So again, here's 2, here's 4. And this is really why I wanted to use u of t as much, because u of t, you're multiplying and you can make these kind of drastic changes to equations pretty easily. I know this is getting a lot more into it than you're probably looking for, but it's the gist of how equations are manipulated. We can use this to get rid of this section of data. And then we might be able to take this part and shift it to the left. So that's mathematically how a computer might look at, okay, I've recorded 5 minutes of audio, I want to take this chunk and this chunk and put them together. That's kind of the equation that I've got. So I've got sound sample 1, all of the information that I don't want, sound sample 2, and then I can take each of these different chunks and kind of smush them together to get the actual information that I want. So, I know we started a little bit late, but we are getting a little bit on. I don't want to keep you guys too long. So, that is the gist of equation manipulation. It's algebra. Are there any questions just off the bat?
Not really. It's pretty straightforward, I guess.
Yep. It's not the most interesting part, but kind of understanding where people get, so say programmers with audio, being able to make those mixed audio signals. Mathematically, this is kind of how it's done. So.
Alright. Right on.
Again, I'm a terrible teacher, but you're stuck with me.
What's that?
I'm a terrible teacher, but you're stuck with me, so this is what you get.
You're cutting out, bud.
That's alright. I have nothing important to say anyways.
You said something about me being stuck with you?
Yep. As a teacher. Even though I'm terrible at it.
Yeah, shut up. Just fine.
So. yeah, I think that's about it. Justin, you still need to get me your homework if you haven't by the time that this is actually up and you watch it.
Justin, I don't care how important this house is, don't miss class.
So, you had to get your jab in.
Oh, sure. I was sending the messages too, so don't worry about that.
So, Kate, do you have any questions?
Do you need me to email you my homework?
Go ahead and, well, yeah, if you can just email me the homework that you did. I suppose we didn't cover that, did we?
No.
Alright, let me open up that homework, because you're right, I completely forgot about that. Charlie, you sent me yours. Charlie, I can hear you typing very, very well.
Yeah.
But yeah, just go ahead and email it to me. Kate, we did cover kind of what we were looking at. The second question, creating a brand new equation for every signal that we analyze, or combining equations. Basically, we covered that with the topic in general today. It's easier to work with equations that we already know and just kind of combine them in different ways to make approximations of our actual data. So pretty much it's like Excel. We aren't matching the exact data that we're pulling in. We're kind of making a good approximation, and from there we can have, you know, Six Sigma and all that away from our data. Create mathematical models using continuous or discrete signals. We create continuous signals from discrete data. So we take points of data and then we match a continuous signal to that data. So that's the gist of it. Short, sweet, and to the point.
I like my love life.
Okay.
I had to throw that in there. It's just a joke. It'll be offended
But-
anybody. I'm sorry.
I think that pretty much covers it. If this is going to be what the next class is going to be, I think we'll be kind of right in that good ballpark for time-wise of the hour. So, do research on the next topic. The wiki is due next week, your section. Anything else that I'm missing? Hopefully we'll be able to have everyone for a class for week 3. But yeah, next week, system properties, and how systems affect signals. I'm going to finish up writing up the questions that I have for homework for you, and I'll get that email to you. There aren't really any resources that I have to share. One additional place for kind of a wide variety of information is Wikibooks, just kind of a collaboration of the different Wikipedia pages and things that relate to signals and systems, digital signal processing, and basically you can follow those, find other resources, and kind of expand upon it. Comments, questions, concerns?
Doing great.
Alright.
Thank you, Kate. That's all I got.
Alright.
Yeah, I don't have any other questions.
Okay. Like I said, I'll get this homework assignment that I'm one question in. It'll only have 2 other questions, so I'll finish that up. Maybe tonight, maybe tomorrow, and get that to you. Alright?
Yep.
Alright. Have a good night, guys.
Bye, everybody. Bye.
There you go, Justin.